Imagine training a neural network to model the continuous evolution of real-world systems, like a patient's vital signs, stock market fluctuations, or the motion of a robot arm. These processes aren't sampled uniformly. Data arrives irregularly. Some values are missing. Noise is everywhere. Traditional models struggle. But neural differential equations, NDEs, were built for this chaos. They treat time as continuous, not discrete, allowing them to handle irregular observations, missing data, and noise with grace. Yet there's a glaring weakness: they can't use dropout. Dropout, yes, the same technique that revolutionized deep learning, is fundamentally incompatible with NDEs. Why? Because dropout in its standard form is a discrete, layer-by-layer phenomenon. But NDEs evolve smoothly through time. So how do you turn off parts of a system that's continuously flowing? For years, researchers have tried to patch this gap, some with jump diffusion processes, others with ad hoc modifications. But none have been truly principled, general, or effective. Today, we introduce Continuum Dropout, a new regularization technique for neural differential equations that's not just possible, but theoretically sound, universally applicable, and naturally enables uncertainty quantification. This isn't just an improvement. It's a paradigm shift. Let's start with the basics. In a standard neural network, dropout works by randomly deactivating neurons during training. At each layer, a neuron has a probability $P of being dropped out, set to 0. This forces the network to not rely too heavily on any single neuron, promoting robustness and generalization. Now, in a neural ODE, the equivalent of a layer is a continuous flow of time. The state evolves smoothly. \frac dz, tdt \gamma tzt \theta. If you naively apply dropout, say, by randomly zeroing out components of \gamma, you're breaking the continuous time structure. You're injecting discontinuities where there should be smoothness. The result? A model that's unstable, hard to train, and fundamentally inconsistent with the continuous dynamics it's meant to represent. Even more troubling, existing attempts to model dropout in continuous time, like jump diffusion processes, fail the most basic test. They don't recover the discrete dropout formula when discretized. So we're left with a paradox. Dropout is essential for regularization, but it's incompatible with the very framework it should help. What if we rethought dropout not as a random mask, but as a stochastic process that alternates between active and inactive states over time? This is the core idea behind Continuum Dropout. We model dropout as an alternating renewal process, a well-known concept from stochastic processes and reliability theory. Think of it like a machine that alternates between running and paused. It runs for a random amount of time, then stops for another random duration. Then it runs again. And again. This alternation happens independently for each component of the latent state. In mathematical terms, for each dimension I$ of the latent vector z, t$, we define two independent exponential random variables. xn I, the duration of an active evolving period. Yn I, the duration of an inactive paused period. These define a renewal cycle: active, inactive, right arrow, inactive. We define a dropout indicator function I\lambda1, \lambda2, t$, which is 1 when the system is active, 0 when paused. This function switches between 1 and 0 at random times, governed by the exponential durations. Now the dynamics of the latent process become \frac dz, tdt equals I\lambda1, \lambda2t, \circ, \gamma t zt, \theta. So when I equals 1, the system evolves normally. When I equals, the state is frozen, no change, no gradient flow. The entire process is now stochastic, but still continuous. This is not a hack. It's a mathematically rigorous continuous time analog of dropout in raised nets. Now here's the beautiful part. How do we define the dropout rate $P in this continuous setting? In discrete networks, $P is the probability that a neuron is deactivated at each step. But in continuous time, we don't have steps. So we redefine P as the probability that a component of the latent state is inactive at the terminal time t. This is known in renewal theory as instantaneous availability. And thanks to the memoryless property of the exponential distribution, we can compute this probability exactly. For fixed t, the dropout rate P is P equals \frac \lambda1 \lambda1 plus \lambda2 \left 1 e \lambda1 plus \lambda2 t \right. This gives us a clean, interpretable relationship between the hyperparameters \lambda1 and \lambda2, the rates of active and inactive periods, and the desired dropout rate P. But we have two parameters and one constraint. So we add a second condition. We control the expected number of renewals, the average number of active-inactive switches, over. Let's call this M. Now we have two equations. P equals \frac \lambda1 \lambda1 plus \lambda2 left 1 e \lambda1 plus \lambda2 t right. M equals \frac \lambda1 \lambda2 \lambda1 plus \lambda2 t \frac \lambda1 \lambda2 \lambda1 plus \lambda2 2 left 1 e \lambda1 plus \lambda2 t right. Solving this system gives us the unique $, \lambda1 \lambda2 for any p(m). And here's a practical insight. M is surprisingly robust. Our sensitivity analysis shows that performance is stable across a wide range of M. So you don't need to fine-tune it. Just pick M equals $10 or $50 and you're good. Now here's the real game changer. Because the dropout process is stochastic, the latent trajectory z, t, $ is no longer deterministic. Each forward pass generates a different path. This means we can use Monte Carlo sampling at test time, just like in Bayesian dropout. For a single input, we run NMC forward passes. Each time we sample a new realization of I\lambda1, \lambda2, t. Each gives a different final latent state z, t, $. We then compute. Predictive mean, \bar z, t equals \frac 1 NMC, \sum j equals 1 NMC, zj, t. Uncertainty estimate, \text var equals \frac 1 NMC, 1 \sum j equals 1 NMC, zj t \bar z t, zj t \bar z t, \top. This gives us well-calibrated confidence scores, not just predictions, but trustworthy uncertainty estimates. And the best part, you don't need a full Bayesian model. This is a plug-and-play method that works with any NDE. Let's compare continuum dropout to existing methods. Naive dropout just applies dropout to the drift function. Ad hoc breaks continuity, fails. Jump diffusion claims to be continuous, but its discrete version doesn't recover the Ray's net dropout formula. Theoretically inconsistent. Steer TABN kinetic regularization, specialized. Not general. Don't offer uncertainty quantification. Neural SDEs add noise, but it's not dropout. They don't model the on-off behavior. Continuum dropout. It's the only method that is theoretically grounded, based on renewal theory. Architecturally universal, works with neural ODEs, CDEs, SDEs, and more. Principled in defining dropout rate. Naturally enables uncertainty quantification. And the experiments prove it. We tested continuum dropout across time series and image classification tasks, including PhysioNet sepsis, predicting sepsis from irregular ICU data. Speech commands, audio classification with 35 words. CIFAR 100, SVHN, SDL10, standard image benchmarks. Across all models, Neural ODE, Neural CDE, Neural LSDE, Neural LNSDE, Neural GSDE, continuum dropout consistently outperformed all baselines. On speech commands, it boosted accuracy from 91% to 94%, a 3% improvement, statistically significant. On CIFAR 100, it jumped from 74.5% to 76.2%. But the most striking result, calibration. We plotted reliability diagrams. Deterministic models overconfidently predict high confidence, even when wrong. But models with continuum dropout produce curves that track the diagonal, meaning their confidence matches their actual accuracy. This is uncertainty-aware modeling in action. And the cost? Minimal. Even with 5 Monte Carlo samples at test time, performance stabilizes. Computation time increases by only 10%, a tiny price for such gains. Continuum dropout isn't just a new regularization trick. It's a foundational advance. It solves the long-standing problem of applying dropout to continuous time models. It's built on solid mathematical theory. It's universally applicable. And it unlocks natural uncertainty quantification without requiring complex Bayesian machinery. This means NDEs can now be more robust, more reliable, and more trustworthy, especially in high-stakes domains like healthcare, finance, and robotics. So the next time you're modeling a system with irregular, noisy, or missing data, don't just use an NDE. Use continuum dropout. Because in the world of continuous dynamics, dropout isn't just possible, it's necessary. If you found this insightful, hit like, subscribe, and share with anyone working on time series, continuous models, or uncertainty quantification. The code is live on GitHub, link in the description. Try it. Experiment with it. And if you're doing research in this space, this is the method you've been waiting for. Thanks for watching. Until next time, keep modeling the world one continuous step at a time.